In this tutorial we're going to be working with a magnetic field in a solenoid. And the first situation that we need to understand is what is a solenoid. And the solenoid, for instance, is you grab a piece of wire, and then that piece of wire which is conducting, you are going to put it like an spiral, right? And that spiral, that is a solenoid, and that will have, for instance, current. And the loops here are very close together, right? So this is, for instance, a wire like an helix whose loops are very close together, and it is the length of the solenoid, for instance, this length is larger than the radius of the solenoid, very, very large compared to this. Right? So let's look at transverse area. This is, for instance, a transverse cut of the solenoid, where we have, for instance, wires that have, for instance, current that go outwards. That's the upper part. So, for instance, the current goes towards the outward, and here the current goes towards the inward. But it's, for instance, a transverse cut of the solenoid. So what it looks like inside the magnetic field, for instance, is something like this, right? Something like this, right? And we're going to be having, for instance, a lot of magnetic field in the inside of the solenoid. So once again, for instance, the current goes outwards towards the inwards, right? Then goes, here it goes outwards towards the inwards, it goes outwards towards the inward. That's how the current is traveling, right? In a kind of helix. Now, for instance, the magnetic field inside the solenoid is very, very large, right? But outside there is not a lot. So here there is no magnetic field, let's suppose that, and we're going to be using Ampere's law. So in this case, or in this sense, we're going to take this Amperial surface, right? This Amperian surface, where we're going to call, for instance, this is going to be, for instance, the section 1, which is that side. Then we have the sections 2, which are this, and the section 3. And in section 3 there is no magnetic field, and in sections 2, both of them, they are, for instance, perpendicular to the magnetic field. So the only one that is parallel to the magnetic field is section 1. In that sense, B dot ds equals mu 0I. The only one that is relevant is section 1, right? So in that sense, that is parallel, right? Then, for instance, we have the same magnetic field, right? And in any given sense, the integral of ds is, for instance, the length L, right? And we have a number of loops with current I. That's, for instance, that n is the number of loops. So this will be, for instance, mu 0 n over L, the number of loops per unit length, times I, right? And this is, for instance, the magnetic field in the solenoid. We can state that n, which is the number of loops per unit length, right, is like that, and we can save this to say this is mu 0 n times I, and this is the magnetic field in the solenoid.